Hey, dear colleagues, hello to everyone. My name is Dmitry Dobrykh. I'm currently a PhD student at Tel Aviv University in Israel. Today, I will tell you about one of our ongoing projects called Compact Ceramic RFID Tag for Omnidirectional Long-Range Communication. Our whole RFID activity started 4 years ago with Russian Science Foundation grant. And through these 4 years, we made some work with such a nice team. And I would like to thank everybody who participated in this activity. So the topic of the project was implementation of new dielectric materials to develop RFID tags with some enhanced characteristics. To introduction, RFID is a method of using electromagnetic waves to automatically identify and track specific tags attached to the object. So typical RFID system consists of a reader device and a special tag or information holders that have some information, for example, identification number. How it works. Reader transmits some radio frequency signal exciting the conductive currents in tag's antenna, and these currents activate the electronics, the chip inside the tag. This chip in active regime switches between two impedance states, and as a result, it modulates the backscattering signal from the tag and imposing the information. Typical example of RFID tag is NFC card, for example, bank card or electronic pass that everyone uses every day. But we are working on a different frequency band, around 900 megahertz. And the main characteristics of RFID tag on this frequency are compact size, long reading range, tolerance to different materials of the objects, especially metal objects, omnidirectional response in space, and low cost. Since we use ceramic materials, unfortunately, low cost is our weak point, but all the other characteristics we try to increase as high as we can. Our first project in this topic was a work published in 2020, and it was dedicated to long-range, compact, passive ceramic RFID tag. So typical RFID tags are usually based on printed metallic meandered dipole antennas, and they have long reading range, but a size around half of operational wavelengths, or they are much compact in size, but due to the reduce of the reading range. So our idea was different. We proposed to use dielectric resonator with high dielectric permittivity and low material losses as tags and antenna main element. On the top of the dielectric resonator, we placed a small non-resonant metal ring with RFID chip soldered in the gap. So reader antenna transmits the signal and excites displacement currents inside the ceramic. And the electric resonator was operating at magnetic dipole mode. And due to the inductive coupling between the ring and the resonator, these displacement currents could transform into the conduction currents in the ring and activate the chip. So chip modulates the impedance, it modulates the current, and through the inductive coupling back, it modulates the backscattering from the whole structure. So we made such work, and later during this project, we do a lot of different another works in ceramic RFID tags. We made RFID tag insensitive to rotation in space, omnidirectional RFID tag, tag for labeling metallic objects, few works about hardware RFID security to prevent data theft from far field, and a few sensors. But today I want to focus on a thematic of omnidirectional RFID tags. In this topic, we started our work as a continuation of our first work with ceramic tag, and we add to this tag a specific plastic holder to solve the polarization mismatch problem. So it is a problem in RFID when your reader's antenna placed incorrectly due to the tag's antenna. And people try to solve this polarization mismatch using reader's antenna with circular polarization, and also they use tags made of cross dipoles, but it's allowed to add additional degree of freedom, but fully not solve the problems. It always has one plane in which the tag cannot be interrogated since it's a planar structure. So our solution was take our ceramic tag and place it in a specific holder, which is placed inside the plastic shell. The holder have 3 legs which touch in the shell, and the fourth contact point is the bottom of the holder. Inside the shell is lubricated to reduce the friction, so the system can rotate freely inside, and using the weight of the resonator, we apply the roly-poly operational principle. So no matter how we can rotate the outer shell, our resonator would be always parallel to the ground. It means if we will fix the reader's polarization perpendicular to the ground, magnetic field perpendicular to the ground, we will never suffer from polarization mismatch. But of course, it's not omnidirectional tag. It's just a solution to solve this problem. And the main advantage here was long reading range. We achieved 12 meters of reading range. As the next step, we made omnidirectional RFID tag, but the reading range was only 1.5 meters. And if we take a look on the literature in this topic, we can find that omnidirectional RFID tags have always low reading range. So what is the reason? To understand it, we can take a look on link budget calculation equations for downlink and for uplink. So downlink and uplink just separate 2 directions of communication from reader to tag and from tag to reader back. And the parameters in these equations are pretty much the same, but there are not so many we can change during development of new designs. So operational wavelengths, transmitted power, and gain of reader's antenna are limited by international regulations, and we cannot increase them. Chip sensitivity and reader sensitivity are limited by the state of the art electronics at the moment, and we cannot also make it better. We don't have qualification for that, at least. All we can do is try to increase antenna's gain, or together with matching coefficient, realized gain. But here comes a problem. We cannot make isotropic radiator with high gain. It's impossible by its definition. So here comes the problem to make omnidirectional RFID tag with high reading range. So is it dead end? Maybe no. Fortunately, we have additional degree in freedom in ultra-high frequency RFID, which is frequency. On that frequency, RFID works not at a single frequency, but in some bandwidth. And inside this bandwidth, reader operates with multiple channels. For example, in the USA, it's 52 channels of 500 kilohertz. So it calls frequency hopping, and it used to keep 2 or more readers from interfering with each other when they try to identify tags in the same area in space. And if we take a look on a spectral analyzer on a reader signal, we can see all these RFID channels. And at some moment, we start to think how we can use it. And some time ago, I had an idea that we can use it to make not an quasi-isotropic antenna, but we can make omnidirectional tag using the whole frequency range. In RFID, we doesn't care if we read the tag on one frequency or another. We just need to read it. And from this point, we can read the tag from different directions using different frequencies. And to realize it, we made a resonator close to a cubic shape, which supports 3 orthogonal magnetic dipole modes, not one. And it supports them on closed frequencies. And to fit all these modes with RFID chip, we add the same metal ring on the edge of this cubic resonator, in that way that we have projection of magnetic field on all 3 axes. It means we can excite all 3 orthogonal dipole modes at the same time. That is the result of numerical simulations. We made close to a cubic shape of the electric resonator, and on the S parameters you can see the resonance cascading, and on the near fields we can clearly see 3 orthogonal magnetic dipole modes. And if we take a look on the radiation diagram, we can see dipole radiation diagram, which along the frequency range is rotating in space. So we need not a cubic shape, but different sides of the resonators to make a cascading. We don't want to excite them on the same frequency, but I will tell you about it a few slides later. At this moment, we need to estimate how we will define the omnidirectivity of our tag. To do it, we made the following algorithm. We can calculate in CST realized gain radiation pattern along the RFID allowed frequency range and extract these diagrams as equirectangular projections, creating 3D matrix of realized gain. So the dimensions of the matrix are theta, phi, and frequency. Next, for this 3D matrix, for each direction in space, we can find a maximum realized gain along the frequency. And for this maxima, we need to make a small correction due to the reader's channel bandwidth. Since we operate not at a single frequency, but in some bandwidth, we need to add, to expand this maximum frequency for at least one RFID channel, and it will be a little decrease this value. So, and from these values, we can create our final projection of realized gain, not at a single frequency, but in the whole frequency range. And if we will see on the results of this algorithm, we can compare the projection of realized gain diagram of at one frequency, which is typical dipole with 2 minima, and in the whole frequency range, which is not a dipole anymore, it's pretty isotropic, and the minimum value on this map will be omnidirectional realized gain of our structure, and we can use it to calculate the omnidirectional maximal reading range. And another not maybe intuitively obvious question, how far or how close we should put our resonances. To define it, we made a parameter delta F, which is distance between 2 side peaks, spectral distance, and numerically changing this distance. We calculated for each iteration the omnidirectional realized gain in a frequency band. And you can see when this distance and small peaks are close, the realized gain is not optimal. We need to shift the resonances until some optimal point. In my opinion, we can think about in the following way. When our resonances are too close, they start interfering, and we don't see 3 different dipoles anymore. We see the superposition of it. And it could be good if we try to create a quasi-isotropic antenna. But in our case, we have different goal, and it's not the optimal way. So we expand our resonances, but if we will make them too wide, between the resonances, we will observe bad impedance matching. And due to this bad impedance areas, we will create weak spots on our diagram. So we should expand the resonances, but keep the impedance matching good along all the frequency range. And a few words about miniaturization. We can miniaturize our tag by increasing the dielectric permittivity of resonator. And the first reason to do it is to decrease the bandwidth, since not all countries have such wide RFID allowed band as America. And for some countries, we need to make it really narrow. But here we can face two main problems. The first is fabricational complexity, since fabrication error becomes more crucial in this way. And the second one is temperature dispersion of high epsilon ceramics. So the tag will be more sensitive to the environmental fluctuations of temperature. So from this point, we decided to make experimental realization with dielectric permittivity of 100, which is temperature stable. Not so long time ago, Ildar and Alena made first experimental sample, and they measured the resonance cascading of our tag. Here you can see maybe that the impedance matching is pretty bad, but it's not a mistake, since our structure should be matched with a real RFID chip, which has different impedance than just a 50 ohm port. And if we will compare it in numerical simulation, we can see that when we have good matching with the chip, we have bad matching with the 50 ohm port. But we still can see the position of the resonances in the spectrum. At the moment, Ildar and Alena try to beat the experimental measurements of radiation diagrams, reading diagrams. At the moment, at the distance of 7 meters, they achieved good results in two sites, but at the last plane, we have a sector with bad reading. Now they try to fix it, and I believe we will need a few more experimental iterations to finish our results. So our goal here is to achieve at least 10 meters of omnidirectional reading, which will be almost one order increasing forward in the area of omnidirectional RFID tags. So it's all our experimental results at the moment. We are actively working on it. So, and it's all for today from me. So thank you for your attention, and I will be happy to answer your questions.
Thank you, Dmitry. Dear colleagues, time to your questions. I have several. First of all, oh, Stanislav, the floor is yours.
I think you was the first one. There's no problem. I can wait.
No. You are first.
Okay, as you wish. Dima, thank you. I have a question regarding the measurements that you have shown at one of the last slides of your presentation. Did I understand correctly that you try to check whether the pattern is uniform of this proposed structure?
Yeah.
But it seems that you do these measurements at quite low frequencies in the environment of this corridor, which is not, of course, an anechoic environment. Could the reflection effects from walls disturb the radiation pattern here?
Yes, you're right, and we're seeing that it is the main problem that we have now during these measurements. So Ildar and Alena try now to book our sports hall, or maybe some other big auditorium where we don't have walls close to our structure to beat these multiple reflections. Now it could be one of the main problems why we have distortions on our diagram. Yeah, it's of course not the fully correct measurements.
I see. Okay. And another question is for this brick of ceramics. It looks like it was composed of multiple plates, so it was not a solid cube, but composed of multiple plates. What kind of material that you use?
Oh, actually, I can't remember correctly the exact material, but it is standard ceramics that Elizaveta Arkadievna did when we order her ceramic around 100 epsilon dielectric permittivity. So she measured exact dielectric permittivity, and she measured the losses at 1 gigahertz for us. So we know the parameters of our ceramic, but not to lie, I will not tell you the exact formula of it, since I didn't remember.
Yeah, probably the kind of calcium titanate.
Yeah, something like that, but I don't remember correctly.
But the color is really surprising, because usually it is brown, while here it is purple.
Actually, when we ordered it last time, it was different. It was like 3 years ago. It was different color at the moment, but after like 1, maybe 2 weeks, it changed color to this purple. But Elizaveta Arkadievna tells us that the dielectric permittivity of this is fine. It's 100. 100, maybe 1, something like that. Small mistake.
Yeah, I didn't know that you can obtain the color on demand. So you can color your ceramics in arbitrary way. So probably it's a good new opportunity.
Maybe so. It's maybe more question to material study of the ceramics. So we're interested only in dielectric properties at the moment.
Okay, thank you so much.
So I have several technical questions. First of all, you was mentioned that the impedance of the chip is different from the 15 ohm. Can you explain what the impedance of your RFID chip?
Yeah, typical RFID chip could be presented as a resistor and a capacitor in parallel. So we during the modeling, we just use the data about this resistance and capacitance from the data sheet of the chip. So and this chip we used is Impigi Monza R6, which has resistance of around 1.5 thousand and capacitance around 1.23 picofarads.
Okay, I see.
So it's pretty different from 50 ohm.
So high impedance matching. Okay, and I have a question about your superposition of different mode. First of all, you show the, if I remember correctly, it was in the 11th slide. Okay. Several slides ago, you show that inside the RFID frequency range, we have more than 15 some channels.
Yes.
And as I understood and as I understand that in different frequency, you have several gain the special. Okay. I didn't understand why you just summarized far field distribution for different mode and claim that this is your directivity.
So about these channels, Reader don't use all of these channels at the same time. He switched between one to another in pseudo-randomic sequence, and we need only to cover only one channel to read the tag.
Okay.
Yeah, that's why we can use this principle if and one frequency our channel covers our tag in this direction. On another frequency it will not, but it will this frequency will cover another direction, and by the sum these all directions should cover the whole space.
So as the result, if the reader cannot find RFID tag at the lowest frequency, the reader go upper at the frequency range and find another mode.
It switches between the channels anyway. Of course, you can change the sequence and ask the reader work just at one frequency. But by the definition, it works by hopping between different frequencies. It's just to avoid interference between several readers. So, and it pretty quick covers all this range. So we need just to wait maybe half of a second to cover all the frequencies, and one of the channels should find our tag. That's our goal.
Okay, I see. And how do you think what's the concept is better? The first one, when you have some rotating RFID chip inside the sphere holder, or the last one made of the cubic ceramic resonator?
I think the last one is better, because when we speak about this rotating holder, it's first of all just not really common shape of RFID tag, and it's twice as bigger in size. And also here we have a limiting factor that we need to fix the polarization of our reader. So it can be used only if we have some gates, reading gates or something like that. But in a general case, this realization is much better, since we can use any reader with linear polarization, with any linear polarization at this moment, and can still read the tag from the same distance from any direction. So that's much better.
Very nice idea.
Thank you.
Okay, dear colleagues, you have a question? Pavel, you're welcome.
Thank you. Hello, thank you for very interesting theme. And can you please open the design, maybe fourth slide, I don't remember, the design of omnidirection.
One?
Yes, this one. Could you please repeat it, because it's not clear for me. And if we look at the upper left, yes, this one. Okay. Is it was taken from some literature, or it's a result of your some optimization work?
Yeah, it's our work made by our group.
Okay. And some of part with antenna is interesting for me. Could you please explain, if we look at the back part where two parallel line goes, what is the aim? The aim is achieve omnidirection, or if we put two parallel line as a rectangle, we reduce impedance. Could you please?
Here, when we try to optimize, we used it to overlap several resonant modes. So if we use just one ring, here we excite only one mode, but with these additional strips, we can tune the second mode close to our frequency. So we didn't seem at the first, at the start, at this antenna as impedance matching element. So impedance matching here is only this T lane, but just to tune the second resonance. And here it is the superposition of two different resonances, and they overlap at one frequency and obtain quasi-isotropic response, but with low gain.
Okay, thank you. And how do you achieve with design? Is there some optimization procedure from CST, and what is the optimization criteria for this procedure?
Actually, we find at the moment some antenna designed for 50 ohm, which was looking pretty similar to this, a bit different, but we started our optimization point from this antenna. Then we add ceramic core to minimize the dimensions. And at this moment, we also tuned the parameters of the antenna to maximize the gain, keeping the overlapping of two resonances at the high level.
Okay, and at first steps of developing the structure, do you solve the problem in free space or in ceramic?
In free space with 50 ohm port.
Okay. Okay, thank you very much. Thank you.
Thank you.
So, you have another question? I think we can finish our meeting. Thank you very, very well from everyone.
Thank
for
you.
participating. See you.